So our next speaker is here, in Dryden, Bayesian analysis, and I wonder if you're going to get raise as many questions as Chris did.
Well, we'll see. Yeah. Okay. Right. Well, thanks very much for the invitation. Very pleased to be here. I'm going to be talking about some joint work. My collaborators are listed there, particularly Huiling Le, who's at Nottingham. Kwang Rei Kim was a postdoc of mine, Wayne Chang, Zhang Shen Huang, and David Hitchcock, all from the University of South Carolina. So I'm going to tell you a little bit about object data first, and then there are essentially three examples I'm going to tell you about. So the first one, analyzing growth curves, the second one about molecule matching, and the third one about phase shape and some regression there. So object data, is a sort of relatively new umbrella term that's being bandied around. If we think about data, data is incredibly important, as we all know. So data-driven discovery is a real buzz phrase, and we're used to, in our early starting statistics courses, talking about count data, measurements, so real measurements, and vectors, multivariate data. So this is the bulk of data that we see every day. Object data are more complicated than that. So where we have data which might be, for example, points on a sphere, spherical data or circular data. It might be a function. So here is some mass spectrometry data. It might be something perhaps in the brain, so something to do with the shape of the brain. It might be on a very small scale, molecule shapes. Here this comes from a representation of movement in the brain from diffusion weighted images. Here's some mouth shape, and here's some landmark shapes. And other things like trees might want to be compared images. So complicated objects, lots of structure, and we want to do statistics on them. We want to be able to perhaps estimate the mean shape, describe the variability of shape, do some regression of not just shape, but functions, objects, images. So shapes are the main thing I'm going to be talking about, and that's obviously what the topic of the workshop is about. So shape analysis, we've heard about David Kendall shape space already, and I like your sweatshirt with David Kendall's triangle shape space on the actual sweatshirt, which is very nice. We have invariances under some choice of transformation. So with shape, we want to consider what's left when we remove translation, rotation, and scale, and that's the classic David Kendall shape space. And shape data usually lie on a non-flat manifold, so we need to take into account curvature. But just as Chris did with the analysis, we will often do a tangent space approximation and then carry out analysis there. So that's the sort of usual approach with shape analysis. But with shape analysis, the geometry can be quite complicated. So these pictures of like spheres are deceptively simple. Shape spaces are often very complicated. The curvature isn't constant everywhere usually. It can be, but it isn't usually. It's usually much more complicated than that. There can be singularities in the shape space. So actually dealing with shape spaces is a difficult matter. So if we think about registration, which is the key thing I want to focus on, we've got many choices of registration and invariances that we want to get rid of. So the David Kendall invariances are translation, rotation, and scale. We might not want to get rid of the scale, so we might just want to get rid of rotation and translation, and that's size and shape space. We might want to get rid of affine transformations. That's sort of affine shape space. And we might want to go further than that and get rid of some sort of smooth deformations. So this picture here is sort of like Darcy-Thompson-like grids where one's transforming. It was a some landmarks on a sooty mangabe, a little monkey skull from the side profile, and this was a young one, and then this was another one a bit older. So they're going up in age. They've been compared, but you can compare them by looking to see how the grid changes. So that's one way of changing shape. So to describe how the actual interpolating grid changes, or one can represent the change by, for example, how it's represented in these shape spaces. And that is the approach, the second one is the approach that I'm going to be considering. Now, shape spaces, as I've said, are complicated, but actually points of landmarks in real space are not that complicated. So, we're used to dealing with real coordinates, and so it may be if we put our models in that space of the landmarks rather than in the complicated shape space, it could give us an alternative way of doing our analysis. A very easy way of specifying models, and as long as we can take care of the invariances somehow, maybe integrate them out, that is one way of dealing with it, or perhaps maximizing over the invariances, then these are two ways we could deal with our analysis. Yeah.
Can you just briefly summarize, give a brief summary, how would you do this grid change based on the landmark? What's the minimal set of data you need in order to get some sensible
Do you mean
transformation, to deduce the transformation for the grid?
Do you mean at each stage, or do you just mean this picture?
So in other words, this is the Darcy-Thompson picture we saw. But
Yeah.
one question is, how did he draw those lines? I don't know. He might have explained in his book. I didn't.
Oh, right. Well, I think he did it by eye. So you get some points in one figure, some points in another figure which are related, so they make sense to compare. They're called homologous landmarks, so there's some relationship, like the tip of my nose is related to the tip of your nose, and so it makes sense to compare those. We could compare our eyes, for example. So
interpolate to have a line to across them. So I normally think conformal mapping, but in this case, you have data to start with.
Yes. So you would map from this grid. You've got a square grid here. You make sure each point gets transformed exactly onto the comparable point here, and then you do a smooth interpolation in between. So this here was using thin plate spline transformation, two of them, one for interpolating the x coordinate from here, and then one interpolating the y coordinate, and then that point gets sent to there, and then you just interpolate.
I see. So you have an array x coordinates, y coordinates in the spline of it.
Yeah, two splines, one for the new x and one for the new y. Yeah. Okay. So, and in this case, it doesn't guarantee one-to-one transformation of thin plate spline, although roughly, approximately, it is in practice often. But if you have a very big change, this doesn't have that. But there's people in this room are very good at much more sophisticated diffeomorphisms, which actually retain this one-to-one property. So, so this is just a simple version of that. Yeah. Okay. So I'm going to talk about the two approaches then. If I have a model in the top space, which is the space of the landmarks, and I called it ambient space. You've heard some of this talk, a lot of this talk before. I think you're the only person here, and I called it the ambient space before, and you criticised me for calling it the ambient space. So, well, I don't know whether criticism is the right word, but we discussed it, and with lots of people, and a lot of people said top space was a better word than ambient space. But
jump,
yeah, yeah, whatever, yeah. So. So the top space is one, and the ambient space is another.
Sorry, Peter.
Right. Right, I've lost my train of thought now after that. Yeah. So here's an example. That's a good way to proceed. Right. We have what this example is a very famous data set in functional data analysis, which describes the growth rates of some, in a study from Berkeley, there's a data set, we're looking at the girls and the boys. This is the girls data set, and the time's been rescaled, but it was from age 1 up to 18, actually. That was the actual scale, but I've just scaled it to 0 to 1 here. So the growth rate, so this is the change in height over time, the derivative of the height. So very large changes at the beginning, big growth change when you're just born, and this was starting at year 1, it's still growing very fast, slows down a bit, and then you can see there's another couple of bumps here, around here, and then definitely a very big bump around here. The usual puberty is being hit here. Now, if you want to compare this functional data, it's clear that people have their change in puberty at different times. So the big spurt in growth when you're 10 or 11 or 12 is different. So if I was just to not take into account of that, just take an average of the curves as they are, I would probably not getting a particularly good average. So it would smooth out a lot of the effects. So it makes sense to take into account some sort of registration of the time, in this case, before I do my analysis. So in this example, the registration is going to be a mapping, one-to-one mapping of the time axis here, so that we align the features of the growth curves. So here are two curves, for example. That's this curve and this curve, and it would make sense if I was going to average them, rather than just at these points in time, to average them after I've matched them up, and then I'm going to get a better idea of the average.
Does that involve local scaling?
Yes. Yeah.
So it's time dependence.
That's right. So the time would be it's a nonlinear transformation of the time. Yeah. Right. So so the time transformation from the original scales, and I'll just have it 0 to 1 everywhere because it's simpler, although it's ages 1 to 18 in reality. So the transformation will be going from here to here, and this is, for this particular example, and I'll show you where this comes from in a minute, is an estimate of the warp and some confidence or credibility intervals.
What's on the vertical axis?
Right, the vertical axis is also time. It's the warped time. Okay, so you're going from the original time to like the new time after they've been aligned. And if there was no transformation, that would just be a straight line, and that might be what you would perhaps your prior, which I'll have in the model, will be a straight line, but we will allow departures from that. Okay, so going back to this notation then, top space. The top space in what I'm going to talk about today in my examples is a standard type of space. So this would contain, in our case, the functions themselves. It's usually a simple metric space, such as the Euclidean space, L2 space, square integral functions, or a sphere, for example, something simple. In this case, it's going to, well, I'll tell you what it is in a minute. Yeah. The quotient space is another way of doing these sort of registration problems, and that's where we look at equivalent classes over the group of transformations. So we've got our original space, top space, and then we quotient out the space of transformations. So Q is usually a complicated space in terms of the geometry, and not usually Euclidean. So it's usually non-Euclidean. So we've got two choices, like with the function one. Basically, I can have a model just for functions, and then have a model for transformations, and look at the joint distribution of both of those. and then at the end of the day, I'd be interested in the difference in the aligned functions. Or I could just align them as best as I could, so I could optimize over the alignment, and then do my analysis there, which will be in this quotient space. And in a quotient space, if we want to look at the distance, so between two shapes, between two objects where we have these equivalence classes, so this is imagine it as a warped function along here. The distance between any two functions will be smallest once I've warped them to be as close as possible. So the distance q in the quotient space is the smallest distance after I've warped one of them to the other, and I want an invariance property that if I warp either of them, I want to have the same distance between them. And usually the geometry of models are simpler in this top space rather than the quotient space. Okay, so in order to do the functional data analysis, I'm going to borrow from the framework of Srivastava et al. And Ian German in the room is responsible jointly for this as well. So this involves, first of all, taking the derivative of the function and then normalizing by the norm of the derivative. And this is called the square root velocity function. And this has a nice property, very nice property, that if you want to compare the original functions using what's called the Fisher-Rao or elastic metric, then you can do that using a standard L2 metric between these functions. So between the square root velocity functions. So basically, you transform your functions just by taking derivative, and then you can do a very standard L2 metric between them. And this has the property that if I've got two functions, if I warp them both by the same amount and then calculate the distance between them, then I will get the same distance. So that's a very nice property. Okay, so for the Berkeley growth data, these are the square root velocity functions. So we've taken the derivative again of the previous functions, and that's what they are. And I want to be able to then carry out my analysis of the data, and I'm going to use a Bayesian model. Okay, so I know we've got quite a diverse audience, so I won't go into too much details with the statistical aspects of the model. So I'll just give you the idea that you've got a function, so you can express a model for a function using the basic model would be a Gaussian process. So basically, any two or any collection of finite points on the functions would have a multivariate normal distribution. That's essentially what a Gaussian process is. So we say that the difference between the two Q functions is a Gaussian process, where Q2 star is the warped version. So you've got one of these square root velocity functions, and then you're warping the other one, which is the Q2 star. So we're going to give it a multivariate normal if you look at a finite set of points. So that's going to be the model for the Q function. And then for the warp, this warping function, which is a parameter that I will also want to do inference about, I'm going to use the following model. So it's going to be a Dirichlet distribution for increments of the warping function. So you've got a warping function. If you've got a finite set of points along it, and you look at successive differences, those will all add up to 1, and they will all be positive. So a natural model for this is a discrete probability distribution. would be a Dirichlet distribution. So it's a model for the warping functions. So we've got a model for the original functions, and I've got a prior model for the warping function. And I can encourage certain behaviors in my prior model. So if I have a Dirichlet model with a large A here, it'll mean that I'm going to encourage the slope to be 1. So I'm going to encourage it not to move too much. If A was a smaller number, just 1, then the warps can be quite flexible. So these, going back to this example, we've got 2 warps here, and this is after the registration, and this was done using this particular model that I've just described, and we ran a Bayesian Markov chain Monte Carlo simulation for the inference, and this is the posterior distribution of the warping function. And if we have multiple curves, which we do with the Berkeley growth data, then we can set it all up in a Bayesian way and do inference on all the individual warping functions, and we have an average curve as well. So again, it's perhaps a bit technical if you're not so familiar with this, but the actual idea is that we have parameters, each of the individual warps, we have the mean, and we're going to estimate them, and we're going to get some idea about the variability as well. So when we actually look at the posterior mean of...
What's the meaning of the constant A?
A. So the A is a prior parameter. If it's very large, then the warp will be just the identity. And if it is small, if it's 1, for example, which is uniform, it will allow to vary quite a lot. So if you have data and curves, and you don't want them to be, you can match curves so that anything matches if you allow it to be flexible enough. But if you want to restrict it so they don't move too much, which is sensible here, I think you don't want to be matching 1-year-olds with 17-year-olds. You want to have some constraints. Then a larger value of A will make sure they don't move too much in the warping function.
In that setting, you are not using the Fisher-Rao.
No, we are using the Fisher-Rao actually. Yeah, we use it for the likelihood, the Q function. Yeah. So this is the.
Oh yeah. Yeah, because this is a model.
Yeah.
No, you use the.
So these are square root velocity functions, and the Fisher-Rao is in the likelihood term. So how close the individual data are to the mean, overall mean. Yeah. So it is being used there.
So you use the L2.
L2 distance, yeah, up between the Q's, yeah, which is the Fisher-Rao between the curves, and then this here 50 is a fairly high number to stop the warping being too strong. So.
But you arbitrarily chosen.
Yes, it's my prior. Yeah. So as with Bayesian analysis, my prior might be different from your prior, and let's just.
And you are both right.
That's right. Indeed, yeah. So you would hope that the choice of prior wouldn't make too much difference. So one would normally use see how sensitive everything is to your prior information. So you would try a few different values, and hopefully it doesn't change too much. If it does, it's a bit worrying. Yeah, but the idea is that usually it doesn't make that much difference.
Your metrics seem to favor the second peak. In other words, you want the second peak to overlap as much as possible. Is that why?
It certainly does line that one up very well. Yeah, and that's the strongest peak. So if you don't get that right, then the likelihood term will not be so big. So yes, it will. Yes, it will. It will try and basically match up the biggest parts of it. Yes.
Does the value A equals 50, is it somehow universal, independent on the discretization that you make on the axis, or do you have to adapt it every time you change the discretization, the number of.
I think you would have to. I think it would be dependent on the discretization.
And you have an idea of the asymptotic.
I don't. Karthik might do actually. He's Karthik in the audience has done subsequent work on the continuous limit of these aspects. But yeah, I personally, I don't. Yeah.
You know, just realizing you already have a growth curve.
Yeah.
That's already a derivative. So
It
if you
is,
get time
yeah.
warping,
Yeah.
should the action not be just a composition action, but actually scale it by the time derivative of the time warp? I mean, shouldn't the natural action on growth
Yeah.
have a density action already, so you wouldn't have to do the square root transform to use the Fisher-Rao?
Well, I think in this case it's the growth rates that are the original function. That's what's important. The growth rates.
No, but if it's a
Yeah.
growth rate, then when you warp time,
Yeah.
it needs to, by the change of variable, you want to scale by the amount of warp.
Yeah, but forget the fact that it's a growth rate. That was the curve you're given.
Okay, so you
There.
forget it.
Yeah,
Okay.
no. But I see what you're saying. I mean, the data came as growth rates. It
Yeah,
doesn't
so
come
you-
as the
you
height.
use- Yeah, so then
Yeah.
you keep it as growth rate, but then treat them like rates. So then the natural action of a warp,
Yeah, it could do it that way. Yeah.
and that would actually make it easier, right?
Doesn't matter whether you warp before or after the square root transform. You warp it differently with another action. You
No,
have
but the
written-
original action, the default action on growth curve should not be composition, but should be composition times.
Yeah, after square root transform it is position.
No, without square root transform, it should be that. That's my point.
It's a good point, actually. Yeah.
Surprisingly.
Because it's a growth rate.
No, it is a good point.
Derivative already.
It's
That's
already derivative, so when you,
Finished growth rate, yes.
Yeah.
so the natural action,
It's on the original ones. Yeah.
yeah.
Yeah. So.
Well, yeah, but there's a configuration space M, and there's a tangent to it, and that's the growth rate. You know, that's perfectly sensible.
Yeah. I think it is a choice that.
It's a derivative of a derivative you are doing. Which
I
is
am,
even
You're doing
yeah.
double derivative
Oh, yeah.
of the original
Even better,
measurement.
even better.
Yeah.
Probably the law is universal, just like Newton's law.
Yeah. Let's discuss this later. Yeah. Yeah. Okay. So this is going back to the growth rate scale. Then this is the posterior mean and the aligned curves after having done that. So go back to there. So with this particular model being in the top space, then the properties of consistency follow from work from Alain and Stephanie Alassonniere and colleagues, and this means that if you have an original mean, then as long as you have enough data, you will estimate that mean consistently, and you can say something about how it varies about that mean as well. If we look at the quotient space registration, so that previously was this top space model. If we look at the quotient space solution, you will try and match them up as close as possible. So you find the best warp, and this solution can be obtained by dynamic programming, and then you will get an analysis, and it at the end of the day, it looks quite similar in this example as it does with many, but you don't get an idea of the uncertainty, so you don't get the credibility intervals immediately, at least with that approach. So which of these two approaches is better, whether to do a top space model or a quotient space model? So the top space model, I think the model is much easier to understand in that you're putting things like Gaussians on standard distributions because you're in usually a standard space, so it's quite easy to interpret it. However, if you actually want to integrate out the transformations. So you've got this, in this case, the Gaussian process, and you've got the warp. If you actually wanted to integrate that out and then specify that distribution, that would be quite complicated. Although you can do it with Bayesian MCMC in a computational way fairly easily. In the posterior mode and the MLE, as I've just said, are consistent. So I think that's a very positive property of this method. And the quotient.
What is the scale? How many pluses?
I think I go up to 2. I go up to 2. The 2 is fantastic. Yeah. Yeah. So 2 points for that. Yeah. So we'll see who wins at the end.
It's like the Guide Michelin.
Yes.
There
Well,
are
no.
3 stars.
Yeah, they have 3. Yeah. So the quotient space methods are biased in general, and from work of Nina and Xavier Penech and you as well. Yeah. And we have also quotients. So that's a negative thing for the quotient space. The quotient space estimator is consistent though for a different sort of mean. If you define the mean directly in the quotient space, then it is consistent. So that's a positive thing. And in our example, in many other examples in general, the quotient space methods are often faster and relatively easy. So there's pluses and minuses, and they are usually fairly similar in the outcome at the end of the day, but there's certainly some positive things about the top space method, which I'm talking about mainly in this time. Now, I've spent a lot more time on this example than I intended. It is the longest example by some distance. I'm very briefly going to tell you something about the other examples. So Bayesian molecule matching, it's a very common task to want to match molecules, and it's actually surprisingly difficult. Its shape is a key property of molecules. It really determines their function and what they do. But as I said, it's difficult. So here's an example where you've got 2 proteins, and these 2 look actually quite similar to visually by eye, and you want to be able to compare how similar they are. So you might have more different ones, but maybe parts of the molecule are in common, and we want to be able to say which parts actually are similar in shape. So this boils down to a molecule being represented by points, which are atoms on the either protein or molecule, and in one, and then you've got a set of points in the other one, and you want to be able to say which of the points correspond. So that is the task with molecule matching. To be able to, if I can find which points correspond, then I can align them and see how close they are. So in this particular example, then the red points here match up with the blue ones. The yellow ones here don't match up, and the green ones don't match up. But we want to be able to find that out for ourselves by doing statistical analysis. So very briefly then, the model involves using a match matrix. So if I've got 2 configurations, a red one and a blue one, and I want to be able to say whether the 2 configurations match, then I introduce a new parameter, which is a match matrix, which will tell me whether or not the points match or not. So for example, here, first row is all zeros apart from a 1 in the third place, and that would indicate that point 1 in the reds matches point 3 in the blues. So these 2 are considered a match. Point 2 in the reds matches well with the 5th one here. The 3rd one doesn't really match with anything, so there's no 1, and the 4th one matches with 1 here again. So this matrix and it will be much bigger for, say, comparing two proteins, is something we want to do inference about, and it's an absolutely huge space. You know, it's combinatory massive space in which we need to find good matches. So one can set up a model in a similar way we did for the curve. So you have, in this case, Gaussian perturbations of landmarks. You have a parameter which is your match matrix, and you also have a rotation and a translation parameter too. And you can do it by a quotient space method, where you just try and find the best match, and then that is your answer at the end of the day. Or you can do a top space model and simulate using Markov chain Monte Carlo and get a posterior distribution for the parameters. So we compared these two approaches with in a set of scenarios to see which one was better, which one got the pluses and which one got the minuses. And so the quotient space model was something that we worked on, and the Green and Mardia worked on the what would be called the top space model. So the performance is quite similar, but not exactly the same. The top space model was less sticky. So what tended to happen with the quotient space model, it went to a local solution and then it got stuck there, and it was hard to get out. So you could throw it out and then it would get stuck on another local one. And whereas the top space model tended to move, go to places, move around, and then go somewhere else. So, however, if you did get it right, the quotient space model got the much higher posterior probabilities of true matches, and that, which is a good thing. But also, the top space model gave a lower posterior probability of a false match, which is also a good thing. So there's a picture which just summarizes this up briefly. So this is the quotient space model here, and these are for comparing two proteins. These are the probabilities of a match using the Procrustes model, and this is the original Green and Mardia top space model, and this is using our version of the top space model, and you can see they're higher for the quotient space one. And then the last thing I'll say is, before wrapping up, is that in another simulation study where these are the true matches here, we got for the quotient space side here, we had very high estimated probabilities of a true match when it was there, but then unfortunately there were also fairly high probability, not quite such high probabilities of there not being a match when there shouldn't be. So the picture should look like the black blobs should go across here, and then the red blobs should all go across the top as well. So the quotient space one didn't do quite as well on the false matches, so these dropped down a bit, whereas this one, the top space model, did really quite well. Even though it wasn't quite as high in, like, when there was a lot of variability, it still wasn't doing too badly. So I think on this basis, the top space model was looking better at the end of the day rather than the quotient space one. Okay, so my time really is up. I'm going to skip through all the others by, I wish I could forward to the end, but I don't know how to do it. So just avert your eyes. Right. Okay. Right.
That was the best part of the talk.
Right, thank you.
That's a big question.
Isn't it the case that if there is really some random process that happens somewhere, it happens in the top space and not in the quotient space? So at least from that viewpoint, the top space not being there.
I would consider that the case, yeah. In reality, it's got to be happening in the top space. Yeah. So it seems more natural to be putting a model there. Yeah.
If there is.
Yeah, I would agree with that.
I agree. There is no real good noise model in the quotient space.
No, I think not.
Yeah.
Yeah. But, I mean, you know, one can, for example, in the classic case of landmark shapes, if you've got points being Brownian motion in the original space, then it is another Brownian motion, but the time rescaled in the quotient space. So you know, you can relate the two in some instances, but generally it's very difficult to be able to relate those two. Yeah. Oh.
You choose.
There was one at the back, I think. Yeah.
Okay. I don't remember. Actually, maybe we don't know what is the top space. Actually.
Yeah.
Anyway, so my question is the following: so would it be possible to combine the advantage of the numerical advantages of the top space and the quotient space for the estimation of the posterior?
Yes, I think so. Yeah, definitely. Yeah. So, to get the mode, for example, from the posterior distribution, and that is often what you end up wanting to do anyway. So, I think you're right. Yeah, that you in practice you do often end up using some quotient space type methods, optimization, to align things in part of your analysis. It often helps. So I think they're not really perhaps quite like that. They give fairly similar answers, and one of my slides that we skipped through showed that the two are quite similar because of a usual Laplace approximation. If that holds, then your posterior mode using that quotient space method will be approximate the posterior mode from the top space model. So yeah.
So I think when you look at growth curves, it's very natural to have the probability distribution on the registration or on the warp compared to the closure space, because of course any rescaling of a growth trajectory is not. My question would be, you had this A parameter, I think it was called A for the prior and the warp.
Yeah.
Can you estimate that from the data? Or is it
I don't think so. No. I mean, for a prior parameter, you wouldn't normally estimate from that data set. It may be, though, that you had some other data before where things have been aligned in a sensible way, and then you could definitely estimate that. So if you had some training data, I think that would be appropriate. But if you only have this data set, then I don't think you can estimate it from this data set and use it in this data set. But if you have some other data, I think you can inform your prior using some other data.
Can I rephrase this question?
Yeah.
What property of the data selects A?
So if you had some previous data, and you could see from your original functions how much they got warped, then you could estimate your Dirichlet parameter from that. Then but from the current data, there's nothing in there. It's a prior. Okay, so you can't say anything about it. It's just you. But you can use your world knowledge or a previous data set that you saw yesterday that you haven't used in this one.
Sometimes you can cross-validate things like that.
Yes, no, you could do that. Yeah, no, I mean, if you want, you could do that, but then you wouldn't be doing a Bayesian inference. but it's still a sensible thing to do. Yeah.
Any other questions? Alain, did you have a question?
Yeah, I had a question about the fuzzy molecule experiment. So here the action is you are considering the actions by rotation and translation.
Yes.
Quotient spaces.
Yeah.
And so, but when you have partial matching, that's dangerous to try to register two shapes. Okay.
But you want to do
think,
it.
No.
Yeah.
I don't really understand how it works in the quotient space in this setting where you have this partial matching, and so you could get some weird, registration. And you said that you had some problem about the.
You do, yeah. So basically,
it's coming from that, the fact that you.
Yeah, you select some points from here that you think match, and forget about the others completely, and then match those, using the quotient space method, Procrustes or whatever, and then so it likes that. The algorithm likes that and doesn't want to move away from there. So you say, oh, well, let's try bringing this one in. And it doesn't want to do that because it's already matching quite well. Whereas if you alternatively use this sort of marginalization, you're much less clear about wanting to be at that point, that match. So you can move away from it more easily.
Yeah.
And you spend time.
Yeah,
you spend a lot of time.
You could have several rotations.
Yeah.
Rotations.
That's right.
You
So
keeping your
yeah. So it helps you to move around. Whereas if you're stuck on that best one all the time, you have to sort of essentially break it in order to move somewhere else, and then you get stuck there. Yeah.
I have a comment to that. So if you have already matched parts,
Yeah.
and if this part has a residual symmetry, you could just use only the residual symmetry to try to match the rest.
Yes.
Well, what a morning.
Okay.
Well,
That's good
we'll
point, yeah.
come back from coffee at 11.
Yeah.
For the next talk. Thank you.